interpreting a graph. So we're just going to think to ourselves. We're looking at this graph, and we're going to answer these 3 questions. How is this graph different from other graphs we have studied? Meaning, what does it have? What does it not have? So what does this graph maybe not have that you're used to seeing on graphs? Kyle?
A title.
There's no title. So this is for A. No title. What else?
It doesn't start at 0.
Doesn't start at 0. Which really links us to there being no increments at all, right? We don't know, is this minutes, hours, seconds? We don't know if this is inches, feet, what this water level means, right?
There's numbers.
So there's no increments to tell us really anything. We just know that the water started here, the level increased, stayed the same, and then it decreased. That's all we know. Yes?
Can I use the restroom?
Sure. Okay, so part B is just what I said. So water is at 1 level. The level increases and stays the same for some time. We can't say minutes or seconds or hours. We don't know. Then the water decreases. So we've got increases, decreases, same level, all those fun things happening in this one little graph that we're not even really sure what's happening here. So let's figure out what it could be. What could this graph represent? So think about a situation where the water's at 1 level, then it increases and stays at a certain level, and then it decreases. Like, when would that happen in life? Like, I have a very vivid idea in my head, but I don't know, you might have something different. So anything you can think of where the water would be at a level, increase, and then decrease.
Oh.
Yes.
Well, it starts here, and then there's a tsunami, and then it all goes back.
Okay. This is Mrs. Marsh. Hi. Sure thing. Bye-bye. Yeah, so again, a tsunami would work, right? The water's at 1 level, this giant tsunami comes, it stays really high for a while, and then it decreases. Okay, any other? Yes. Okay, so your water bottle level is here. You go to the little water fountain, you fill it up, and it stays there for a while, and then you get thirsty and you drink it. Good. Anything else? So you can write down one of those 2 things. You can come up with your own. What I think of is a bathtub, right? So like your water's here, and then when you get in, remember you displace that water so it raises a little bit, and then you hang out for however long you bath. I don't know, I don't take baths. And then when you get out, you start to drain the water, right? So it decreases. So a few different options you can think of there. Right? Or maybe like the last few weeks when we have big rain, like, did anybody get like one of those like rain rivers in their backyard between where the yards meet? Like there'll be this like little creek that shows up.
We have a rock river in our backyard. It's made to flood when it rains.
Yeah, and then it just like goes away into the drains and stuff. But yeah, so any of those things could be a situation that could be represented by that graph. All right, so that's kind of where we're headed. We're looking at graphs and we're trying to figure out what's happening and also like what scenario could be happening. Most students really like this section of functions. So now we're going to specifically look at different graphs and figure out which of these scenarios would match these. Okay, don't mind this over here. You can cross that out. That was just when I did a screenshot, I couldn't not get those little letters in there from the book. So on your own, you're riding a bike. Match each situation with the appropriate graph. Explain your reasoning. You don't have to explain anything right now. Just figure out which uppercase and lowercase go together. Okay, so by yourself, you're looking at the graphs, you're reading the scenarios to figure out which is which. Go. By yourself. Well, you have to read the story. So, like, which one matches with you gradually increase your speed, then ride at a constant speed along the bike path, then you slow down until you reach your friend's house. Right? So, which one would that go with? Nope, I don't want you to tell me. You guess. Write in pencil, and then we'll talk. Okay, who thinks they know which graph A would go with? Gradually increase, ride at a constant speed, then slow down until you reach your friend's house. What do you think it matches with? Kyle?
C, wait, yeah.
Yep, this would be, well, here, I'll put lowercase a. Yep, that definitely goes with this. So you increase, stay at the same speed, decrease. Right? All right, how about B? You gradually increase your speed, then go down a hill. You then quickly come to a stop at an intersection. Jack?
A.
It is A. Okay, a lot of people struggle with this one because you want the words to match what's happening in the graph, but this is showing speed, right? So if you're going down a hill, doesn't your speed increase? So it looks like you're actually going up a hill, but this is about your speed, not your elevation on a hill. So that's a hard one sometimes for students to be like, wait, I'm actually going faster here. And then you quickly come to a stop. So your speed slows down really fast. So that's why this goes down at such a steepness, right? So this is actually going down a hill. Let's circle this and write down a hill. Right? Okay, so we have A and B spoken for. How about you gradually increase your speed, then stop at a store for a couple of minutes, then you continue to ride, gradually increasing your speed again. Which one do you think that matches? Where you would actually stop? Chandler? Yeah. Right, increase, stop. This is when you're at the store, your speed isn't changing, right? So there's nothing happening here while you're there, and then you increase your speed again. So then, of course, this leaves D. You ride at a constant speed. You go up a hill, right? So you're going to slow down while you're riding up a hill. So that's why, even though this looks like it'd be a downhill situation, this is actually your speed. So right up a hill. What was that, Kyle? It looks backwards, but remember, this is measuring speed, not elevation.
Is that the case for all of them?
Nope, because if this was measuring elevation, then our graphs would look totally different. But this is just how fast you're going on your bike. And then you gradually increase your speed again. You guys having fun yet? Yeah, this is great fun. This is easy peasy, Mrs. Marsh. Okay, comparing graphs. All right. We've got two graphs here. We're talking about height above the ground and the time. We've got graph A and graph B. We still don't have any increments, so we don't know if this is minutes or seconds. We don't know if this is feet or inches or miles. We don't know. Okay. One of them represents the height of a rocket, and the other represents the height of a water balloon after they are launched. Okay. Weather balloon, not water balloon. Weather balloon. Okay. How are the graphs similar? How are they different? How are they similar? How are they different? Chloe?
They're both graphs about height above ground.
Yeah?
One is straight and another is curved.
Yeah. They measure the same things. One is linear. The other is not. Okay, compare the steepness. So what do we see here with the steepness of these graphs? What do you notice visually? Nothing? They're exactly the same? Hmm?
We're going up.
They're both increasing. Okay. Are they both at constant rates?
No.
Sure aren't. Nope. So graph B has a constant steepness, right? Graph A clearly doesn't. It curves. Okay, and this is where we get into a little bit of a debate. Which graph do you think represents the height of the rocket? So which one do you think represents a rocket being launched versus a weather balloon being launched? Keegan?
B is for rocket.
Why do you say that?
Because the rocket just goes straight up.
Okay.
Doesn't like go around.
So you're thinking that the rocket would be, the elevation would be higher faster? Is that what you're saying?
Yeah.
Then the weather balloon would just slowly increase over time?
No. The rocket can change, but the balloon will just go up at the same speed. Because it will change.
Why do you think the rocket would change?
Because it will run out of gas.
Okay. So are you thinking that maybe this one would then like slow down and no longer be linear, or are you thinking that now maybe this one is the rocket one?
That one. Number A is the rocket.
I mean, you could really argue it both ways. What do you think, Aiden?
A.
A is the rocket?
Yep.
We all see it differently. And I have asked Miss Pattison this in the past, like which one she thinks it would be. I don't remember what she said. I feel like she said this one would be the rocket for some reason. I mean, obviously for what you guys said too, but that this would just...
Bill Nye the Science Guy said that too.
Bill Nye did?
Yeah.
Oh, I love Bill Nye. But most think A. Okay. All right, we've got something similar here. We're comparing graphs again. Oh, do you guys need more time to copy that? No? All right, so we've got two cars. One car is approaching a stop sign, the other is approaching a yield sign. Do you guys know the difference between a stop sign and a yield sign? I mean, you're not ever driven. Okay, what does yield, I mean, I think we all know what stop means, but what does yield mean? Slow down and?
We have to let the people go
Use caution.
Use caution, right? So, when I was growing up driving, like you only really yielded when you were like getting on or off an exit. But now, I mean, in Hamilton County, we have to yield all the time because what is Hamilton County known for? Roundabouts, right? You slow down. Sometimes you have to stop if there's a car coming, but sometimes you just keep going, right? So your powers of yielding, right, are a lot stronger because we have to do it all the time for all those roundabouts, hundreds of them, right? Okay, so we can put here roundabout, right? So this is kind of like the one we just did. How are the graphs similar? How are they different?
Same measurements, one is linear, one is
Yep. Only this time they are decreasing, right? Rather than increasing.
graph B is a constant.
Say that again.
Graph B has a constant.
Yep. Graph B is constant again. Bless you. Okay. We know that by that straight line. All right, and which one represents a stop sign?
Graph B.
So one of them you come to a complete stop no matter what, right?
Yeah, graph B.
Yeah. If you want to get a ticket your first year of driving, don't come to a complete stop at a stop sign, and you will get a ticket immediately.
Thanks
Alright,
for the
I'll do
advice.
that.
I'll follow.
I'm just saying.
No top, no stop.
It's like the police officers know you're a new driver. Like they have some kind of radar or something. Like not like a radar, like speeding radar, but like they just know. And then they're gonna watch you like a hawk to try to teach you a lesson. So don't let them do that.
What lesson are they giving us when making us pay a whole bunch of money?
That you should have come to a complete stop. That's the lesson. Right?
I mean, but who wouldn't come to a complete stop at a stop sign?
A lot of people.
People in a hurry, people who think, well, there's no cars around. That's when they like to get you.
Well, to be honest, I feel like it's not really that big of a deal if you don't stop at a stop sign if there's no cars around you. I mean, like, if there's no cars around you,
I
don't
would
stop at a
love
stop sign. It's
to
not
watch
like
you
a
have
lot
that
of-
conversation with a police officer. Love it.
Cam could win that.
You
I
think
don't
so?
think I would. I don't think I would win that.
I don't think you're going to do it, but I'm just saying, like, they're going to be like, well, I'm sorry you don't feel that way, but here's your $400 fine.
$400.
$400 for
Listen,
stopping at a stop sign?
Yes, because that's where, like, most
You
accidents
have
happen,
$400 on you?
is people who don't stop at a stop sign. All right,
Sounds good.
moving on. All right, we've got some more graphs. We've got temperature over time. Again, we don't know what time or what the actual increments here are. We have Oregon and Maine, so that's like northwest, northeast. Okay. So describe the change in temperature in each city. So what is happening in Newport, Oregon?
The temperature goes down over time, stays the same, and slightly increases.
Yeah. Temperature decreases. Then stays the same. Then increases. Right? Decreases, stays the same, increases. I would love, you know what? Do you know if on weather apps, if you can go back and see how much the weather changed?
Oh, man.
On Safari.
I'm not 50 years old.
So, like, I have, like, 4 weather apps because I'm kind of obsessed. But, I took my dog on a walk last night, and it was almost warm out. And then I woke up this morning, and it was opposite of warm. So I would love to know the temperature change. Like, it had to be drastic. Because it was 57 last night, and it was like in the 20s this morning. That's a big change. Okay, what's happening here in Maine?
Temperature increases.
Mm-hmm. Was there any time when the temperature stayed the same?
No.
Nope. Thank you. I will zoom out. There we go. So do you guys ever like look back at elementary school? I don't know if you're far enough removed, but I have a story from elementary school about the word temp instead of writing out the word temperature. Do you guys want to hear it?
Yeah.
That's what I'm writing.
What, the whole word or just temp? Yeah. So I was in 5th grade science with Miss Craig. We rotated for science, and so I was in Miss Craig's class. And we had to do a project, and it had... That was this teacher's name.
Was she a guy?
Her name was Miss Craig. Her last name was Craig. Okay. So there was a project we had to do, and it was evaluating temperatures. I don't know. And we had to do like a report with one of those like fancy plastic like protectors with the little thing that like keeps it all, and like you had to write it on lined paper. You know what I'm talking about, Amelia, right? It was super fancy 5th grade work. So throughout the whole thing, I just abbreviated temperature, the whole thing. And I turned it in, so proud. And then like 2 days later, when she decides to talk to us about the assignment, she goes into this whole ordeal about taking it up. Students who take it upon themselves to abbreviate words, they should never abbreviate. I mean, she just like lost her mind. And I sat there knowing she was talking about me the whole. She never said my name, but I knew she was talking about me the whole time. So to this day, what is that, like 30 years later, 31 years later, every time I write the word temp, I think of Miss Craig, like being really upset that I abbreviated it.
You're still alive.
Why was she so mad?
You should go say hi to her.
I don't know where she is. I mean, she may not even be alive. It was 31 years ago,
Oh.
right?
Yeah, she probably isn't.
I don't know. But she was super upset about it. Like super.
How old was she? Like 78?
I don't know how old she was. I never asked my teachers how old they are.
She got that mad over a word?
She got very upset. Very upset.
Karen.
Okay,
For a Karen teacher.
here we go. We're going to match up the description to the part of the graph. So this one doesn't even have increments. We'd have no idea what this is measuring, right? No idea. But we need to find which section represents something staying the same. So which one do you think that would be? F, right? So then cross off F. So you guys do the rest of that by yourself. Figure out which sections match each part of that graph. You can do it. I have faith. I'm going to freeze my screen and then I'll...
Describe their relationship between tuning quantities.
You okay?
Gotta use restroom.
Okay, do you guys need more time or are we good? Everybody thinks they have it ready? Okay, here we go. Increases at an increasing rate. That can be a little confusing. This is the increases at an increasing rate. That's when you have a curve. So if it decreased at a decreasing rate, that would be curved as a decreasing value. How'd you guys do on these?
5 out of 5.
Notice that we have quickly increasing, meaning it's steeper, right? Versus slowly increasing, which is not quite as steep. They're still at constant rates, so you know that they are straight line sections, but one is slow, one is faster. Anybody get them all right? Okay, we're moving right along. You guys are doing awesome here. The last page. And they're doing fantastic. Describe the relationship between the two quantities. Okay, so we have a balloon. We have volume of the balloon and over time. So what's happening here?
I
Right. Isn't that what happens when you blow up a balloon?
Yeah.
Right? You blow up the balloon, then you take a breath. So it's the same for a little bit, and then you blow up the balloon some more. Right? So we could say increases constant rate. Stays the same. Increases. And then I'm just going to put dot, 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 because it's just going to continue over and over again. What would happen if, what do you think happened if all of a sudden the volume is just like empty? What do you think happened?
Let all the air out.
Okay, but how?
Open the balloon.
No, if you opened it up, it would decrease gradually. What has to happen for all the air to be gone instantly? Pop it, right? And sometimes my boys, my youngest especially, he's really proud of himself that he can blow up a balloon, but he never knows when to stop. So I know that one day he's going to get like balloon plastic in his eye because it just like pops every time. It's kind of scary. He'll figure it out. Okay, how about this? Dollars over time. So we have sales, and we have something happening with money over time.
it decreases at a constant rate and then it increases slowly.
Yeah, they quickly decrease, right? Because it went, right? So quickly decreases. Then slowly increases. I like to call this like the Chipotle graph. How many of you like Chipotle? I mean, I love Chipotle. So, but there was a time when Chipotle was not very popular because they kept having like health issues for people who ate there. right? So their sales dropped dramatically. Like people just like stopped going because they didn't want to get sick. But they have been able to rebound. It took them a while, but they've been able to rebound slowly, right? By proving that their facilities are clean and those were isolated incidences. Chandler? It should say then slowly. Thank you very much. I don't know a whole lot about engines or horsepower or speed, but I mean this graph is pretty self-explanatory. What's happening here? Horsepower is increasing.
It's increasing.
And what happens when your horsepower increases?
It goes faster.
What's happening here? What's happening in this section of the graph? Does anybody know?
It's going up
So
more
it's
than
changing gears.
Changing gears. Who said that? Nice. Changing gears.
No, it's good.
Anybody have been in a car where someone's driving manual? Like Jeeps, a lot of Jeeps are manual. And you have to like change gears, and so it's like it increases really fast, and then it tapers off again, and then it increases, you know, right? Horsepower increases, and so does the speed. Can you guys see that? There you go.
cars powered by horses.
That's how it's measured. I don't know who decided that, but somebody a long time ago. Because, you know, horses used to actually be what powered people getting around places. Carriages. Horses and carriages. Yeah.
You know, the thing where it's like
The more
that's
horsepower
carried
you
by
had, the faster you could go in your carriage.
I was going home from a camping trip one day, and I saw a bunch of Amish people going down the road with their horses. There was like a big, huge truck behind the Amish person. But the truck was literally just sitting there and it didn't move.
Probably. Yep. Were you in northern Indiana?
Yeah.
That's where Amish country is, in northern Indiana.
Northern Indiana.
Okay, we're looking at the decay of something over time. Exponential decay here, right? So it quickly decreases. At a decreasing rate, which is, you know, kind of confusing, but that's just what it is. That shows us that it's curved. Just like that part of the graph that was increasing at an increasing rate. All right, what's happening here? Hair length. This is our graph of it.
Growing.
What's happening at this point right here?
It's getting cut.
Yes. That's just like if the balloon popped, right? It instantly decreases. There's like not even, you can't even draw a line for it. It's just gone. And then it grows back at a constant rate, and then it's gone. It grows back at a constant rate, and it's gone. Then haircut time. Right, just the same thing like when you mow a lawn. Grows, grows, grows. Cut, it's gone. Maybe it grows faster at certain times of the year or slower at certain times of the year. Not your hair, the lawn. Well, I don't know if hair grows at different rates.
It goes slow.
I thought you were growing it out.
I was, but I'm now I need a haircut.
Did you tell him to just get a mullet?
No, no way. I am not getting a mullet. The mullet's trying to happen. There's a mullet that's trying to happen, but no, I'm not going to let it happen.
Yeah. Okay, last one. What's happening here for a loan? You have a balance on your loan, like what you owe somebody, and the payments.
They're paying it back.
Yeah, this is probably the day they make the payment every time. So they have this much and they pay. Now they have this much and it stays the same because you don't pay anything while you're waiting for the next payment, right? So loan value stays the same. Then you make a payment. New loan value stays the same. Then you make a payment. And then the new loan value stays the same until you get to 0, which is a good feeling. Great job today, guys. Put this in your jam behind the notes from last week. This does count as a note that go in your table of contents.